Alright, so in this particular video, we have, it says in the figure, a block of mass M hangs at rest. The rope is fastened to the wall, is horizontal, and has a tension of 52 newtons. It says the rope that is fastened to the ceiling has a tension of 91 newtons and makes an angle of theta with the ceiling. And then it wants us to find the angle and the mass M. So here theta is touching the ceiling, and then M is the hanging mass. Alright. So in order to do so, the first thing you should do is draw all your tensions in these types of diagram. The first one I want to do is I want to draw the tension that is in the left string, which is pointing towards the ceiling, because that is the surface in which the string is tied to. And then I'm going to label what I was given. T1 is 91 newtons based on the statement. And then notice that T1 is a diagonal, so it has to have components. So therefore, T1 is pointing left and up. So I know T1x is going to point leftward. T1y is going to point upward. But what I like to do is I like to use the horizontal axis as my reference point. So I'm going to move theta down here. This theta that's touching the vector T1 to the horizontal, aka the ceiling, is labeled as theta. So therefore, this theta that I have in red here is also the same angle. Okay. Next, we are going to call this tension that's attached to the wall T2. Again, it doesn't really matter what you call T1 and T2. I've chosen to go from left to right or clockwise in this case. T2 in the diagram is given as 52, or in the wording is given as 52 newtons. And then last but not least, the weight of the box is going to be pointing down the page. F of G, force of gravity due to the mass of the box. The weight of the box is mass times gravity. So therefore, that's that. In order to find theta and M, we need to figure out what this triangle is. So if you keep looking up here, T1 is a diagonal, aka the hypotenuse of this right triangle in red that I've drawn. We already know the hypotenuse, which is 91 newtons. So therefore, in order to solve for theta, we need to know one more of the legs. We either need to find T1y or T1x. And I think for this one, the easiest way to find is T1x, because as you notice here, there are only two x arrows. One pointing right in blue, one pointing left, which I've labeled T1x. So without overcomplicating it, right away I know that T1x has a magnitude of 52 newtons. Or to be proper, we say that T1x is negative 52 newtons pointing left. But I'll do the work here just to show you what it looks like. Because it says the system is at rest, net force in the x direction is 0. So therefore, if you identify correctly, we have a vector pointing right, which is T2. We have a vector pointing left, which is T1x. So I can say positive, which is T2. I like to do my positive first. T2 minus T1x. It's minus because T1x is pointing in the leftward direction. And then from there, I can solve for T1x simply by moving T1x to the right side. Negative T1x is going to turn into positive T1x. But what I do know is that T2 is equal to 52 newtons as stated. So therefore, right away, I know that T1x is T2, or the magnitude. So once again, don't let this mislead you. T1x, the magnitude of T1x is 52. But we know that I introduced the negative sign earlier. So really, T1x is negative 52. Or I like to tell you, use common sense. T1x is pointing left, so it's got to be negative. Okay. So what we can do is we can transfer this top right red right triangle down here. We know the hypotenuse, aka T1, is 91 newtons. I just found T1x, which is 52 newtons, or negative in this case. But here we're just trying to find the angle, so it doesn't really matter whether you label the components positive or negative. The angle is just going to be using deduction. All right, T1y, I'm going to label. So right away, the angle here is given, which is the same as this right triangle that I initially drew for you. Here to find theta, we have two legs. We have the adjacent leg and the hypotenuse. So right away, even though I don't know what T1y is, I don't really care. To solve for theta, all I need is two of these legs. I have the hypotenuse, I have the adjacent. So therefore, hopefully your geometry is good that it triggers cosine, y cosine, because I know the adjacent leg and then the hypotenuse referencing this theta. Okay. So therefore, by definition, cosine of theta is adjacent over hypotenuse. Adjacent in this case is T1x, hypotenuse is T1. Therefore, to solve for theta, we do inverse cosine. Well, T1x in this case is 52 newtons. And then T1, given in the diagram, is 91 newtons. And if you punch it in your calculator, you just get a value of 55 degrees. So theta here is 55 degrees, okay? So the red theta is 55 degrees, therefore the black theta in the diagram is 55 degrees. So if you want to be proper, you can say that this theta here is 55 degrees south of the positive x-axis, okay? Referencing the ceiling, of course. All right, other than that, if it doesn't matter, 55 degrees is your theta. All right, that's the first part of the question. And then the second part is what is the mass of the hanging mass? So therefore, to solve the hanging mass, hopefully it triggers the hanging mass has a weight, and the weight of this hanging mass is in the vertical axis. So therefore, you need to focus your attention in the vertical axis or along the y direction. So here I have my work net force in the y direction is also equal to 0 because the system is not moving. Well, if you look at this diagram properly, we have two arrows that are pointing up in the y-axis, or just pointing in the y-axis. T1y is pointing up, f of g is pointing down, T2 is a perfect horizontal axis, so it doesn't have any y component to contribute to this particular problem. So once again, we have T1y pointing up, f of g pointing down. These two arrows have to equal in magnitude in order for the system to stay still. So here I'm going to write the positive quantity first. T1y is pointing up, so I'll write that pointing up or first, and then f of g is pointing down. So once again, I introduce the negative sign right away in my work. I want to subtract that from f of g, and that's equal to 0. So moving f of g to the other side is going to look like this. Once again, T1y, if you kept up with the work, T1y is the opposite leg, and opposite in this case would be sine of theta. So sine of theta is equal to opposite over hypotenuse. T1y here is hypotenuse times sine of 55. 55 I got from my previous work in calculating the angle. And then negative mg will be moved to the right side of the equal sign, which turns into mg. And then from here, we can just divide by g in order to find m. Okay, so the second part of the question asks you to find mass. So hopefully by now, your algebra is good, that you recognize in order to find m, you divide both sides by g. T1 is 91 newtons, because that was given to us in the statement here and in the diagram. And then sine of 55, well, 55 degrees, we just calculated it in the first part of the question. And then here in the bottom, you notice I put 9.8 meters per second square. It's not negative 9.8 because I've already accounted for the negative sign in my work. Okay. Not only that, even if you put a negative sign, you need to know that mass is a scalar quantity. So therefore, mass cannot be negative. So hopefully that triggers like, oh, you did something wrong, or you introduced a negative sign that is not appropriate. All right. So if you simplify this on your calculator, 91 times sine of 55 divided by 9.8, you should get a value of 7.61 kilograms. So that is the mass of the hanging mass. And that is it for this particular problem. All right, good luck, stay nerdy, don't be whack.